What I'd like to do is see if there are any questions or concerns about how things have gone so far in the smells lab. Are there any questions? Is everyone getting access to sapling? Is everyone able to figure out how to get their answers in their notebook and so forth and so on? Hopefully you'll learn that the fastest way to get answers to your questions will be through your GSI in your section. And if you have questions regarding like the lecture materials, perhaps content that may be on the exam and things like that, you can direct questions to me. If you have trouble getting into sapling, there's a sapling technician. I put his email address. His name's Tony or Anthony, and he's available. He's from San Antonio. That's where the system, I guess, is. Yeah, if there are any Texas fans here. That's where the system's set up. So he's really in control of sapling. So if you have to change sections or anything like that, or you're having trouble accessing them, please contact Tony. If you have iClicker problems, or you're wondering if your iClicker is working. I'm sorry, last Friday we didn't do an iClicker question. It didn't really count anyway. I was just trying to get a sense for how well the clickers are working. We'll do one today. It's going to be very basic and pretty trivial. But if you have any questions about your iClicker and whether it's working or not, there's a B space set up for that. Okay? And I understand that people have problems the first couple of weeks, but then by next week, hopefully everything will be settled and everyone will have time to obtain a clicker. And remember, it's just a trivial portion of your grade. Okay, if there are no questions, then we'll get started. So the lab this week is going to be looking at polymers. And the question might be, well, what is a polymer? Now, polymer is a compound. Oh man, sorry. I have to calibrate. For some reason, the way the display works on Fridays is different than the way it works on Wednesdays. Okay. Anyway, a polymer is a compound, a chemical compound, with a repeating unit. So, a way to represent, say, what is a unit of a polymer? Well, I'll just show it as a bead. We call this a monomer. And if you, add together monomers, you could produce, say, a dimer. Anyway, if you repeat this process, then of adding monomers many, many times, I don't know how you like to represent that, then you get a polymer. This should be pretty intuitive if you've taken any basic biology courses, because there are many biopolymers. And this could be quite long. Another way of saying this might be some notation like this that represents, say, that this is the repeating unit n times. So this repeating unit, in this case, which is a bead, is repeated. And that's what we'll use. Well, that's the sort of notation we use to designate polymerization in chemistry. So there are many kinds of polymers aside from the biological polymers like nucleic acids and proteins and polysaccharides that we come across, common polymers that we come across around the home. And so these are, like I say, ripe areas for all kinds of green chemistry applications to make, say, substitutes that are more environmentally sensitive for some of these products, or new ways of forming these products. One of them is polyvinyl chloride. We'll get to the structure of this in a minute. But this is found in things like hoses and, for example, shower curtains and things of that sort. PVC, yeah, that's what PVC stands for, polyvinyl chloride. And polystyrene or PS. And you might imagine different places like takeout containers. This is the foam that you see in coffee cups and takeout containers. It's not that PS is inherently foamy. It's actually, some gas is blown into it to make it puffy. But it can also be a solid, crystalline material. There are some clear polystyrene takeout containers and also like utensils that are made out of polystyrene. So this is the new competitor of polystyrene is polylactic acid, which I say is the green competitor, which is PLA, abbreviation, polylactic acid. Remember in the last lecture we tried to introduce the concept of enantiomers, or stereochemistry. We had handedness. And if you just flip two groups around that central stereocenter in lactic acid, then you make its mirror image. And if you polymerize those lactic acid molecules, you get polylactic acid. And it's found in biodegradable products like cups and forks and things like that. It's a little bit more flexible than polystyrene. It doesn't hold up to heat as well, but those are drawbacks for biodegradability. Polystyrene does not break down so easily. Polyethylene or PE is I think the best way to think about it are milk jugs. But that's sort of the higher density polyethylene, which is very strong and rugged, so it can hold a gallon of milk. It's stable to pasteurization temperatures. But lower density polyethylene is made of the films, saran wraps, and things like that we put on food. You see wrapped around meat. Obviously, the property is completely different. It's not very resistant to heat, and it's much more pliable, but useful for wraps and things like that. Okay. And then a nice polymer that's used a lot in textiles is polyethylene terephthalate. Polyethylene terephthalate is abbreviated PET. That's the number 1 plastic. Whereas high-density polyethylene is number 2 plastic. Those are the two major plastics used in packaging. And a Coke bottle, obviously a plastic Coke bottle. In the old days, they used to be made out of glass when I was a kid. But now they're made out of PET. And PET is also used to make polyester thread used in textiles. Okay, so it's a very useful polymer. So those are chemical polymers, and you have biological ones. And the reason I put down some biological polymers are that of course we're thinking about green energy and green chemistry, and so these are of course naturally produced and may come into play in these types of applications. Of course, the big one is proteins, and proteins are made of amino acids. These are the monomers made of these monomers. Amino acids, and then there's deoxyribonucleic acid or DNA made of nucleic acids. Polysaccharides, like starches and cellulose. Cellulose is, of course, a really interesting renewable feedstock material considered heavily in green chemistry as potentially a source for biofuels. Anyway, polysaccharides are, of course, made of sugar and sugars. And another interesting one are polyisoprenes. And polyisoprenes are made of, obviously, isoprenes. But you may not be familiar with these things. But think of rubber, natural rubber, latex. And these materials are produced by plants and can be extracted and used for natural sources of rubbery materials, useful materials. Okay, once everyone catches up, then we'll get into some chemistry of polymerization chemistries. Yep. Oh, no thanks. Yeah. I'm actually intolerant to gluten, so that's okay. No, not yet. I'm watching you now. Okay, so so now we're going to consider, say, different types of polymers, and we're going to consider in the types of polymers are basically two different primary mechanisms of polymerization. Okay, so we'll just start out looking at polystyrene. So styrene looks something like this. Remember our line bonding notation from, and you can. So this is styrene, and if I were to be very careful about it, and I wanted to show where all the hydrogens are, I could put the hydrogens in. And you'll notice that I'm obeying my rules of construction here. And each of these carbons, the nodes here, have 4 bonds so far, except for these 2 ends here. So anyway, this is a styrene monomer. I'll write monomer up here. And in order to connect, to polymerize these into polystyrene, to make polystyrene, yes. Basically, what we need to do is initiate this reaction by creating radicals in a small population. So you have to imagine in a beaker, if you're going to make polystyrene in a beaker, that you have a small percentage of these we want to activate and form a radical. Okay, so we're going to do, and don't worry about how this happens, but you might say, well, what's a radical? And essentially, a radical will be, remember when we talked about our non-bonding pairs of electrons, a radical is a single electron. So imagine on that outer carbon there, a single electron. If we drew in our hydrogens, we still have hydrogens in all the appropriate places we had before, except that one spot is missing a hydrogen. And instead, it's a single unpaired lone electron. That guy is extremely reactive. Okay? So if you put him next to a regular old styrene monomer, then what happens is it's so reactive that basically these electrons can jump in and form a bond between these adjacent monomers. And effectively, if we think about this radical electron, it's going to then jump out to that outer double bond system in the new monomer, and you'll get a product that looks something like this. And I'm going to stop drawing in the hydrogens. You'll have to just believe in them. And that's the key. And you'll see that when I did this, maybe I will draw in hydrogens because we're just starting out here. But you can see that what happened is that first double bond with the radical in it on the left turned into a single bond. Okay? Because that pair of electrons that was in the double bond then jumped over to form a new bond to the adjacent monomer, and then that unpaired radical, that crazy electron that's highly reactive, jumped out to that outer double bond system. Okay? And so yeah, if we want to think about the hydrogens, they're there. They're good. Sorry, I said I wouldn't, but and if you count all these hydrogens, you'll find out that no hydrogens were lost in this. The initial hydrogen was lost to the catalyst that produced the radical. Okay, that guy's somewhere out in space for the moment. But when these two guys join together, all right. So if you just do this process over and over again, then you'll end up with a polymer. And one could represent this, by drawing out this big long structure, or they could just shorthand it, like I was doing before with beads, and basically show something like this, and shorthand this notation like this. And this would designate polystyrene, effectively. Okay. Of course, in reality, you see something like this, and on and on. Anyway, and then you could just put these sort of squiggles on the end, and sort of designated. It's not quite infinite, but extremely very long. These polymers. That's my cell phone trying to listen to me, talk to me or something. Sorry. Okay, let's put it over here. So that's styrene, and PVC is very similar in certain respects, of course, because what I forgot to mention was one last thing, and I'll put it in here. That this is an addition. This type of polymerization is called an addition polymerization. Okay, that is its name. Okay, and you can see how that chemistry works. Now, with PVC, we start out with this monomer, which is called vinyl chloride. This is an N, vinyl chloride. And, again, a double bond. Instead of, 4 hydrogens around that double bonded a pair of carbons, we have actually 3 hydrogens and 1 halogen, which is chlorine. And through the similar radical chemistry, radical formation and propagation and so forth, you'll end up with a polymer that looks like this, with a chloride on every other position along the backbone of this polymer. Okay. So yeah, if you think about where the hydrogens are, again, the hydrogens are there, not drawn, in the simplest rendering of that structure. And we won't show much more for PVC, but again, the type of polymerization that we're doing here, because we're doing radical formation and we're doing addition polymerization. Okay. So that is one style of polymerization. I'll just leave that at the top. Now, when we consider PLA, polylactic acid, we start out with this lactic acid monomer. Okay, now I'll try to consider all these lone pairs also in my drawing. Okay. And, this is an interesting reaction. So if I have a pair of these guys next to each other and I have appropriate... Yes? Question? No? And I have a pair of these guys near each other, and I'm in water, or a solvent so they can mix, then turns out this can be catalyzed generally well under acid or base conditions. Then what could happen is that I could basically, let's think of this. I'm sorry I did that to you, but I want to leave a little bond between these groups. So basically, if these electrons come over here, and this creates this very electrophilic negatively charged oxygen, then it can come in and attack the backside of this carbonyl, the carbon, okay, and do an electrophilic attack. And then these electrons that are on this OH group can come off. So when we do that, we're going to get two different. We're going to get basically, in addition, we're going to add these two lactic acid monomers together. We're going to release an H plus, a proton, okay, and we're going to release an OH minus. And so this will create the OH minus, and this will create the H plus. So I'll just put that over here. Got an H plus, and this will have an OH minus. And minus. Why is it a minus? Well, if you look at this, you only have one bond to oxygen, okay, and oxygen normally has two bonds when it's uncharged. If you only have one bond, and you have those, of course, those three lone pairs, then you end up with a -1 charge, generally designated as a minus sign in a circle like this. Just didn't show up well here. That is negatively charged, and this proton is positively charged. Normally, protons like to make one bond, and this proton's making no bonds, and so it has no electrons, so it's essentially positively charged. All right, so the net product, then, of this reaction is oops. Yep, so these are all the lone pairs. And the key thing is, of course, that there's one H2O. Okay, so this is called a condensation, polymerization. Okay, so if I join together n groups of lactic acid, then I make n-1 waters. Okay. So those are basic polymerization reactions. Hopefully everyone's caught up. Any questions on these? Question in the back? Can I go over how what? How the radical is formed? Well, you would add some sort of reagent that would favor radical formation, so it would remove a proton with one electron on it and leave behind the extra electron that was formerly in that CH bond. Those are various reagents that favor this sort of thing. Is that sufficient? Oh, why is that, the green arrow? Well, I mean, I'm just trying to say, it doesn't need to be there. I mean, that extra electron is going to want to move into some kind of orbital system where it's most delocalized. And the most delocalized environment for it to be in is in that double bond system on the end. So it'll naturally want to hang out there more often. All right. So now we're going to talk about properties of polymers. As you can see, there are a diverse number of chemistries that can make polymers. And that means, of course, they've got many different kinds of properties. And some of these properties are good for certain consumer goods, and some are better for others. So one of them is sort of, like I say, the clarity of the plastic. And it turns out that plastics that are sometimes more ordered are more crystalline, are actually less clear, they're more opaque. And plastics that are more disordered, meaning how the different polymer chains interact with one another, are in fact more clear. Okay, you think of like a glass window actually is actually not very crystalline. And that's one key property. Another one, of course, is bendability. You might contrast this with its brittleness. So a key feature of plastics relative to some other materials is that they're actually very pliable. And this can be useful. Sometimes plastics will bend and they'll be able to snap back into shape. They're quite strong. And this has to do with the degree of cross-linking, where the non-covalent forces that are holding together the polymers may be stronger in certain cases than in others. Of course, solvent resistance is something key to think about. Solvent resistance. And also heat susceptibility. So solvent resistance, certain plastics are tolerant to certain types of solvents, but not to others. And generally, when a new polymer is made, they'll try a whole series of organic solvents, including strong acids and bases and oxidizers and the like, and see how those plastics hold up. And it's difficult to predict those properties, although these days I'm sure that they're much better at it. But at the end of the day, it's empirical. And so you'd want to use a plastic that can hold the solvent that's placed in the container. For example, if you had an acetone jar, you wouldn't want to use polystyrene to hold it. The container would just melt. Okay. And the idea there is, again, that each polymer chain has non-covalent interactions that are allowing those chains to interact with one another and create the integrity of the plastic. But if the solvent can get in between those interactions and solvate those polymer chains, then the material will tend to fall apart. Okay. And the polymer chains will be solvated. This is a little bit different than actually using some chemistry that putting something inside of this plastic container that actually damages the polymer chains, reacts with the polymer chains. That's slightly different than this idea of solvent resistance. That'd be sort of chemical resistance. So the heat susceptibility is another issue. Again, you have molecular forces holding your polymers together, and if you heat them to a certain temperature, those molecular interactions may disrupt. Okay, and whatever solvent you have in the container may then solvate those monomers, and the material will then begin to soften up and fall apart. So this leads into the idea of thermostability, and it's actually a useful property to be able to heat up a plastic and reshape it. And those kinds of plastics are called thermoplastics. Thermoplastics, you heat them, and then you can reshape or mold. And so, you could take like a mold and then take some heated polyethylene, inject it inside this container under high pressure, and then create a milk jug. Okay, that's a thermoplastic. So that would mean that things like PLA and polyethylene